Welcome to the discussion of RLC circuits. What we're going to do is we're going to take an RL circuit and an RC circuit and put it together, and we're going to study what happens. So we know that in an RL circuit or an RC circuit, the reactance goes the opposite way and certain things happen. Well, what happens when we put it all together? Like, how do they interact with each other? Well, that's what we're going to answer here. So let's just jump in here and take a look kind of from the start. I just want to back up a little bit and talk about RL and RC circuit. So in an RC circuit, what's going on here is that we know that current leads voltage. And we know that because as the voltage increases here, current is really high because this has very little resistance to current. And then as it gets full, it resists the current more, and then the voltage drop across it actually increases. So what's happening is that the voltage goes up and the current goes down because, well, once it's full, the current doesn't flow anymore. But at that point, the voltage is really high. So we know they're out of phase. When we draw the way that we draw the current and the voltage is essentially we just draw them at 90 degrees out of phase from each other because that's exactly what's going on. Over here, what happens, as soon as we power this up, this thing, as soon as any kind of current goes through here, it produces back EMF and its resistance goes up. And that resistance indicates, essentially slows the current down. And because the current is, slowing down, what happens is the current is slow at first, but the voltage drop across that is really high because it acts like it has really high resistance, or it resists the current really high. And that's because of the back EMF. If you want to know a little bit more about how that works, go back to the lecture, last week's lecture, on RL circuits. Okay, good. So that's what's going on here. And these are 90 degrees out of phase, so the current and the voltage are out of phase. But we indicate that the current and the voltage, although the 90 degrees, it goes the other way around. Yeah. So the voltage across this goes up that way, and the voltage across the capacitor goes down. That's important because as we move forward, we're going to see that those kind of intermix in some way when we put everything together. Now, still, a little bit more review. Let's just continue with the review here. We know current leads voltage of the capacitor. It looks like this. And what I want to do is I want to highlight that we can not only study current and voltage out of phase, but we can study the resistive nature of these elements and say that they're out of phase as well. So I'm just redrawing this phase diagram over here, and we can indicate that this is R here and this is XC. And of course we know XC stands for reactance, or specifically capacitive reactance. Again, the arrow goes down, and in this case, in inductive reactance, the arrow goes up. And again, it's 90 degrees out of phase. So that's what's going on. Now, just in this situation, I just want to indicate that when we put a resistor in here and we put a capacitor in or an inductor in series, the current that's going through the resistor is exactly in phase with the current that's going through the capacitor and or the inductor. It's just, the current's really high at first here and the current's really low at first here. That means the current through here is low and the current through here is high as well. So just to kind of keep that in mind, that the current is not out of phase between these, but the voltage drop across these is actually different. Okay, let's just move on a little bit more. What we're going to do is we're just going to say, well, when we have this resistance, which is the resistance of the resistor, and the reactance, which is the resistance of the inductor and or the capacitor, do we just add them together? Well, no, we have to vector sum them, right? We have to use vectors to add these up. And we know that Z is like this. So now depending on if the resistance is longer or if the reactance is less or more, this triangle changes and the angle changes. And we know that there's a formula to calculate that, but that's not what we're going to focus on. I just want to say that we have to add these as vectors. Well, we continue that theme when we put these things together. And what we're going to do, we're going to put them together and we're going to be studying the impedance, the total impedance, right? Because we want to know what that total resistance is, and that's called the total impedance, or just actually the impedance. And then we're going to study the phase angle. Just like going back here, we know that if this increases more, this angle is going to change and or less. The same thing is going to happen with an RLC circuit. We also have a phase angle. We're going to use essentially the same formula to calculate that. And then we're going to look at this thing called resonance frequency. I think if anything, this is kind of the newest thing that we're going to be looking at. And by the way, this is not a lot of work. It's not a lot to wrap your head around. We already have the theory of capacitor reactance and how it interacts with a resistor. We already already understand the theory of inductive reactance and how it, interacts with a resistor. What we're going to do is we're just going to put these together, and really the formulas and the concepts aren't going to change, although we're adding one thing. We're adding this kind of sweet spot, the resonance frequency, and we'll talk about what that means later. But at resonance, we'll see that when we calculate Z, there's actually, it's just R. I mean, there's no capacitive reactance or there's no inductive reactance when a circuit is at resonance. It's pretty cool. And we can also say VR is equal to Vs when we're at resonance. It's pretty cool. I mean, it's a really interesting concept. But by the way, I mean, there's a question just like this on the exam. So it's just be like, well, if a circuit is at resonance and the voltage source is 100 volts, what's the voltage drop across the resistor? 100 volts. Yeah, it's pretty cool. And you will see why that is true in a minute. Let's move forward and just take a look. Just a little bit more review. But what we're going to do is we're going to add them together really quickly. Okay, so we know that an RC circuit, current leads voltage, and an RL circuit, voltage leads current. So how does that all together? Like, what do we put it together? Well, we need to use these vector triangles to actually these phasor diagrams to figure it out. Now let's just stop and pause and talk about this. Current through the resistor, capacitor, and inductor is the same. Right, it's important that we understand that. The current's always in phase. It's never like you can't have more current going through the resistor and less current going through the capacitor. They're in series. Right? The voltage drops are not in phase. This means that the resistance and reactance are out of phase for sure. And capacitors versus inductors, reactance vectors are an opposite direction. And seems like I can't spell R. Okay, so moving forward, let's actually put a circuit together and see what happens. So when we're drawing this phasor diagram, what's happening is that because we know my XC and my XL are opposite directions from each other, well, we just add them up. I mean, they're in the same line. We can add them up, just like a number line, like a 5 and a 6 and a 12 and an 87 are all in the same number line. We can add them together. Because these guys, reactants, are also kind of on the same number line going up and down. We can just add them. Now, they're opposite to each other. We know that because they're out of phase. So when we actually add them together, we use a pretty cool formula. But, let's just pause here for a second. Okay, so this is our circuit, RLC circuit. And we know this is 1,000 ohms. We know that this guy is 600 ohms and this is 200 ohms. So I know that I just can't add 1,000 and 600 and 200 together because these guys are out of phase from this. And although these are on the same kind of number line, they're completely out of phase from each other. Yeah, they're 180 out of phase. So because they're 180 out of phase, they actually cancel each other out. So what I'm doing is I'm going to add this by taking this all the way down here and coming back up. So if this is 600 down and that's 200 up, then I'm left with this here, and that guy is going to be my X total. So the total reactance is the difference between the capacitive reactance and the inductive reactance. No matter how you look at it, it doesn't matter if one's greater than the other, it's just the difference between the two. When a capacitor and an inductor are in series, the total reactance of them is the difference. It's the difference between the two, and we use this formula. It's not a complicated formula, right? All we're doing is we're just finding the total. Now, it's the absolute. And you could actually do XC minus XL. It doesn't actually matter. But it's the difference between the two. And then if that particular difference is negative, it doesn't matter. Just make it a positive. Okay, there's a couple of other formulas here that you recognize. And this is no big deal. You know this formula here. The only difference is instead of using XC or XL, we're just using X total. And then this guy is not a new formula to you either. So that's how you find your phase angle. Again, we're not using the XC or the XL, we're just using the X total because the X total just looks like this. It's actually this is the X total here. So the impedance triangle is this guy here. These aren't actually part of the impedance triangle. They just make up the math to get the impedance triangle. Okay, good. So moving forward, applications. This is really big. You know that there are a lot of inductors after the power grid. Okay, so the power grid is supplying power to a lot of inductors and actually things with capacitance as well. And that creates a problem actually, because if your current and your voltage are out of phase from each other, then when you calculate power, because power is just voltage times current, if they're out of phase, it creates this weird thing that it creates inefficiency in your power. So what we do is the grid puts huge capacitors and huge inductors into the grid together. So all of the motors that are running in the world on the power grid that actually have a lot of inductance, they don't really cause a huge effect onto the system because these guys are just these huge inductors in the system. So all the motors, they're just kind of, they become a small portion of it. If we didn't have these, there'd be a lot of, inefficient power going on when we were running inductors. Again, because the current and the voltage are out of phase, and power is voltage times current. What I want to do is I want to take the same circuit and I want to put it through different frequencies and analyze it. So we're going to take an RLC circuit, we're going to put it through different frequencies. This guy is going to be 500 hertz. The same circuit is going to be operating at 2500 hertz. And we're going to look at how the inductive reactance and how the capacitive reactance and also how the impedance respond to that. Okay, let's move forward. So we're going to do some math here, okay? So now this is interesting. In this case, if we do the math, I've just done the math here. We'll do them later, but just believe me, this is the math here. If we do the math, the R is going to stay the same. And then the XC, in this case, at a very low frequency, the XC is going to be very high and the XL is going to be pretty low. If we crank the frequency up, we can see that this changes. This goes down and that goes up. But more specifically, look at this. It's interesting. Even though this frequency changed quite a bit, these guys are almost the same value. And that's actually, we'll see that a little bit later when we look at a chart. And also, if you want a little bit more, delve into this a little bit more, there's a great video on the worksheets for this lectures class. And if you watch that video, I explain that a little bit more in depth. So let's just move forward here and we can see that this happens. So this guy decreases and this guy increases as we go along, because as the frequency increases, the capacitive reactance goes down and the inductive reactance goes up. There you go. So this is a more capacitive circuit because this is high. So at a lower frequency, this guy is more like an RL circuit. And at a higher frequency, this guy is more like an I just said RL and I lied to you. At a low frequency, this is more like an RC circuit, and this is more like an RL circuit at higher frequencies. So it's interesting how the nature of the circuit becomes either a capacitive circuit or an inductive circuit depending on the frequency. Obviously, as the frequency increases, it's going to go more towards inductive, and as it decreases, it's going to go more towards capacitive reactance. We can see that they act inversely. Okay, there you go. So let's just moving forward, and there's a whole little chart here, and I think it's important that we do this. So if we take a look at my XC, it does this, as you know, and my XL does this because it's linear. Okay, that's fine. So let's actually analyze the kind of the quarters here and what's actually going on. So if we take a look at this, if I'm in resonance, and if that is actually a frequency that's kind of that sweet spot, where if one goes up and the other goes down, and the other goes down and the other goes up, there's got to be some spot in between where they're actually equal to each other. And that is called resonance. And we will discuss that later. But when we're at resonance, what's happening here is that this is true and this is true. So actually, when I find that sweet spot right there, they equal each other. It's pretty cool. And then when we do that, something really cool happens to the impedance. But for now, let's just see, well, what if my XL was greater than my XC? Well, that's over on this half of the graph over here. And if my XC is higher than my XL, then we're over on that side of that graph over there. Cool. So there you go. Now, let's actually take a look at an example. Those numbers that we had before, I said I calculated them. I'm going to show you how I calculated them all. So here we go. Let's just walk through this. I've got the exact same circuit. We're going to study the circuit at 2500. Right now we're just looking at it at 500. So I've got 500 ohms. Hertz, pardon me. I've got 1000 ohms over here, and then I've got these values here. Now I want to know what the capacitive reactance is of this, and I want to know what the inductive reactance of this. I'm just going to use the formulas. I know them. I'm just going to plug the numbers in. Here I'm putting this to the -1 because it saves me putting 1 over or something, and that's how I'm doing it on my calculator anyway. So I put my values in and I come up with this value here. When I do my inductive reactance, because I'm at a really low frequency, it's probably going to be a capacitive circuit or an RC circuit, and in this case it is, because my inductive reactance is much lower than my capacitive reactance. Now, I need to find the total so that I can continue and find the impedance and the phase angle. So I'm going to take the total and I'm going to find the absolute value. I'm going to take this, the difference between this value, and that's my absolute value. In this case, it's 520 ohms. Now, let's take a look at finding impedance and phase angle. These formulas are no different from what you've been using already. It's just, in this case, I'm just using X total. So I'm going to put these values in and make sure that you put brackets and your number and your unit, because not only are we squaring the number, that is not just squaring the number, it's squaring the unit, because I'm putting 0.5 here. I'm putting to the exponent 1/2, which is really the square root. I mean, I could put a square root symbol there or a 0.5. I'm just putting a 0.5 there. But my point is, if I'm finding the square root of the numbers inside here, and I know my final answer is just going to be ohms, well, then I better make sure that the ohms inside is ohms squared. You have to do the math with the units. Okay, good. So again, math with the units here, ohms and ohms. Even though they cancel out, you got to write them down. You have to prove, you have to show proof of your calculations. 27.5. Okay, let me draw the triangle for this. Now, we know that it is a capacitive circuit, therefore my capacitive vector is going to go down, and then I just put it together, and here you go. So that is the phasor diagram here, and there you go. I got 27 degrees in here, and that's my Z, and I'm just indicating everything I need to do. Now, let's kick the frequency up to 2500 and see what happens. Obviously, it's going to become an inductive reactive circuit. So I'm just doing the math here. All of a sudden, this guy went down, this guy went up, so my capacitive reactance went down and my inductive reactance went up high. I'm just finding the difference again, and I'm writing that down, and I'm going to go over again here, and I'm going to take a look at this. I'm just writing these numbers here so I know how to put them in here. Doing the same thing here, making sure I square my units as well as my values, and my Z is 1193, and over here is 33, and in this case, I know that my inductive reactance goes up, so when I draw my triangle, I draw it like this. Now, I just thought it was interesting to note that this value here, 1193, and this value over here, 1127, are pretty much the same value, even though the frequency was quite different. We'll study that a little bit later, but that's just interesting to note. So moving on, let's just take a look at this. What's going on here is that I've got my XC here, and my XL is here, and that is, depending on the frequency, the circuit can appear either inductive or capacitive. So in this case, I'm dealing with an inductive circuit because my RL is greater than my RC. And looking at this graph over here, what's going on here is I can see that at 2500 hertz, this guy is much higher. My XL is much higher. So this is an XL circuit. Good. So let's take a look at another example. We're going to kick the frequency way up. We're going to go to 10,000 hertz. So in this case, my capacitive reactance is like 33 ohms. It's next to nothing. But look, my inductive reactance went up really, really high. I mean like the 3,000. That's really high. Again, same formula here to find the total inductance. I'm just going to put this together, find my absolute value, and then here I'm going to do this math over here. Same thing. I'm finding my impedance, and my impedance, these guys are almost the same. Well, that's because this is so small, right? If I went up to 100,000 or 2 or 3 or 500,000, pretty much this is going to be the same as this, and it's going to be pretty much an inductive reactance. The capacitance is just going to have very extraordinarily, it'll be like 1 ohm. It'll have no effect on anything. Good. I need to calculate the angle, and I put this in here. Make sure you put X total here, because that's what we're after, right? Okay, good. So now it goes up, and I know that, and my impedance triangle is just going to look like this. Again, like I said, this value and this value are very close, so this is going to be a really long vector, and this will also be long as well. So when I kick it up really, really high, well, that's what happens. So now let's throw Kirchhoff's voltage laws into this. It's a series circuit, so we should be able to study how Kirchhoff's voltage laws apply. And we know that Ohm's law can apply in here as well, but Kirchhoff's voltage law are going to apply as well. Okay, so let's just take a look. This is pretty cool. Watch this. Now, I know that the voltage across the inductor looks like this. Okay, that's the voltage across the inductor. And then I'm going to do this. I'm going to say, well, the voltage across the capacitor is actually 180 degrees out of phase. It's just like this. Now, when I put them together, I get this. And we can see that I'm just adding them up. I'm just adding the values up on this graph here. And in this case, I know that the voltage drop across here was a little greater than the voltage drop across here in its magnitude. So I'm left with a little bit of this. And now I'm looking at a circuit that is inductive, because this is a little bit higher here and it's higher into the inductive range, right? It goes up closer to here. If these guys were exactly the same, this green line would actually be right down the middle. And that's when we have resonance. Pretty cool. So let's move forward here and we'll take a look at this graph here. Now this is really cool. So now watch this. Now I've got these two and they're exactly the same. This is what happens. It's so cool. Watch this. This is what happens. The two of them together look like this. It's just like this. Actually, they completely cancel each other out. The voltage drop across the inductor and the voltage drop across the capacitor are exactly the same values, but opposite in phase. They're 180 degrees out of phase. So they actually cancel each other out. Really? Yeah. There's no voltage drop across the two of them together. Each one has its own voltage drop, but because they're out of phase, they cancel each other out. And technically, really, there's no voltage drop in the circuit at all when we're at resonance across either the inductor or the capacitor. And the entire voltage drop actually is across just the resistor. Now watch this. This is really cool. Now, if I've got this and this, if I'm at that resonance frequency, whatever it is, however you find that, I don't know, just play around with it. Now, there's actually a formula for that. We'll take a look at that in a minute. But when they're exactly the same, that sweet spot, when you turn the frequency, they're equal, just exactly equal, what's going to happen is that the voltage drop across here and the voltage drop across here pretty much cancel each other out. So the entire circuit, all of the voltage in the entire circuit drops across just the resistor. And therefore, whatever the voltage is of this, the voltage across here is going to be the same. It's pretty cool. So what's going to happen is that VR is going to be equal to VS at resonance because these guys cancel out. So therefore, there's really no resistance reactance. Here, the total reactance is zero because they cancel each other out. So there's no reactance and we don't have to add any phasor diagrams at all. It's just resistance and that's it. So therefore, it's just like a circuit with just one resistor and one source, AC source. That's it. These guys don't have any effect on the circuit at all. They're really, really cool. So in this case, my VR equals this, and in this case, my IT is just VR divided by Z. Now I have to use Z. Even though, really, if you think about it, you could kind of put an R there because there is no capacitive reactance and there's no inductive reactance. They're canceling each other out. But because they're in that circuit, we really do need to use Z. Because at some point that frequency could change and then there would be a total, somewhere would sneak in that total reactance would either go into the impedance range or the capacitive range, but we'd have to use Z. So we're just going to use Z because there's either a capacitor and or an inductor or both into the circuit. Cool. So this magical frequency is calculated by this. That sweet spot frequency is calculated by this. It's just 1/2 pi and the square root of LC. No problem. So we just do the math here and we'll take a look at this. What's the resonance frequency of this circuit? Well, I'm going to put this number and all of these together, and it's 196 kilohertz. So if I crank this thing up to 196 kilohertz, exactly, then all of the voltage drop is going to exist only across the resistor. There will be no voltage drop across this and no voltage drop across this. At least there will be, but they'll be completely out of phase and they'll just cancel each other out because Kirchhoff's laws say that. It's perfect. It's beautiful. Now we add up the voltage drops like this. We vector sum them, right? Because they're completely out of phase from the resistor. But it doesn't matter because they cancel each other out. That's it. They're just cancel each other out. Good. moving forward, let's just take a look at the resonance and just doing a little bit more of Kirchhoff and taking a look at this. So what's going on here is that these guys, the voltage drop across here, the sum of the voltage drop across zero is zero. Therefore, all of the voltage across here is going to be here. So if I had a question, what is VR? What is the voltage drop at resonance? Well, it's just 5 volts. This is 5 volt source, and they're 5 volts because there's 0 here and 0 here. And that's it. I mean, it's really nice and simple. So really what we've done here is we've analyzed the fact that when we put them together, when we put an inductor and a capacitor into the circuit together, what's going on is that they interact with each other, and essentially the inductive goes this way and the capacitive goes this way, and we add them as vectors together, and then we get the total reactance. And then from there, it's no different from an RL circuit or an RC circuit, because that total reactance is either a capacitive reactance or it's an inductive reactance, and then we just add it up. And we know the only other thing that's kind of extra that we've been studying is that sweet spot, that's that frequency to find that exact center. So what does that look like on this cool graph? Well, what's going to happen here is my Z is going to do this. Now the interesting thing is, when I'm at resonance, because essentially my reactances just cancel out, I'm only left with a resistor. So therefore the total resistance of the circuit is just the R, the total impedance of the circuit is just the R. Actually, and it's going to be at its lowest value, because the total impedance is only going to be the resistor. There's no capacitive inductance and there's no capacitive reactance. So there you go. I just said capacitive inductance. There's no capacitive reactance and no inductive reactance. So therefore that's, or at least they're equal to each other, so they cancel each other out. So the total reactance is 0. So therefore, the total impedance of the circuit is just R. And at that time, it's its lowest value. It's its lowest value, where Z equals R. At the lowest value, Z equals R. So there you go. This is a really cool chart. Now, moving forward here, let's study this a little bit more, and we'll take a look at what's going on here. Now, if I have this circuit working at 100,000 kilohertz, okay, it's a capacitive reactance circuit. So over here, this is my value right here, and that's going to be at 100 kilohertz down here. The next one, where I'm gunning that sweet spot, so I'm now dialing this up to resonance. At resonance, what's going on here is that Z equals R, and this is the lowest value right here, because these are equal to each other, because at resonance, XL equals XC, and they cancel each other out. Now, if I kick it up to 400, then I'm over here, and I'm dealing with this guy. I'm dealing with this guy over here, where my XL is much higher. There you go. So that's what's going on, and this example, current is essentially, the current is doubled, right? The current is doubled, because if I take a look at this, my current here almost doubled. My current here is 130 milliamps. Over here it's 130 milliamps. Here it's 200 and some odd milliamps. So almost doubled, but it certainly goes up. So at resonance, the current goes up. It's pretty cool. So let's just take a summary of what we just talked about. So essentially what's going on here is that capacitive and inductive, when they're equal at resonance, okay? So when a circuit is at resonance, the capacitive reactance and capacitive inductance are equal to each other. The total impedance is minimum, and it's actually entirely resistance. The impedance is just resistive in nature. There's no capacitive inductance, and there's no capacitive reactance, and there's no inductive reactance. It's just resistive. It's just resistance. And the current is at maximum as well. The current is at maximum when we're at resonance. Now the phase angle between Vs and Is is 0. There's no phase. Nothing's out of phase. Voltage and current are now on the same line. There's no phase angle at all. And we know that to calculate that, we're going to use this formula. And that's it. I mean, that's all you guys have to know. So we really haven't, the only thing really that we've learned is this whole resonance thing. Everything else hasn't really changed very much. So I think you guys are good just to go ahead and do the homework and look at the worksheets, because the worksheets have, like, I don't know, I think it's a 15 or 12-minute video or something unpacking me going through a bunch of examples. But I think you guys will be okay with all of this because you've done all this before. Yeah, that's it. Okay, bye.